All right, so let's take a look at some more statistic stuff. We'll talk a little bit about the central limit theorem. All right, so here it says, have you ever wondered why we use the sample statistic x bar to estimate the so-called average value? Why is it preferred over the median or the mode or other measures of central tendency? We say that x bar approximates the population mean mu, but it turns out x bar does more than just approximate mu. Repeatedly calculating x bar from different samples actually becomes a random variable whose mean is mu, no matter the underlying distribution of the data. The result is known as the central limit theorem. We will introduce some sample statistics and focus on the distributions of sample mean x bar and sample standard deviation s in these next two sections. All right. So we'll explain that more when we get to some of these examples down here. It says a sample statistic is a value that can be calculated from a set of data. Interpreting data and making decisions based on analysis is a job many people do full-time in different professions. There's so much data in the world which is analyzed every day, but what does it mean to analyze data? We need to know what we're calculating and what it means once we've done so. We see that a sample statistic is not known until we have data values. Thus, there is randomness involved in sample statistics. Thus, we will treat sample statistics as random variables. Here we introduce three commonly used sample statistics. So if we got x1, x2, all the way to x sub n are independent random variables with the same probability distribution, then we defined the sample mean as x bar minus 1 over n times the sum of the xi. So that's real simple. Just sum all the x values, divide by however many they are. To be the sample variance, okay, we've got s squared is 1 over n minus 1 times the sum of x sub I minus x bar squared. I goes from 1 to n. And then, of course, the standard deviation is just the square root of the variance. All right. So these, you commonly see these in high school or even elementary school in the case of sample mean. Note here that to calculate S, we need x bar. Intuitively, we see that the sample mean gives each data point some equal weight in the process and calculates a new value that we say is average. The sample standard deviation is like the actual standard deviation, calculating a sort of expectation away from x bar. In this case, as for the n minus 1 in the denominator of s and s squared, the reasoning varies from author to author, and further investigation is left to the reader. So we're not going to get into all that. You can Google it online and read about that. All right, so let's look at this. Suppose the population we consider is the set of all Instagram users. The random variable we want to study is the number of times a user checks their Instagram feed per day. Assume we have the following data. All right, so what we have here is we have the average, we have the mean, and we have the standard deviation. Now keep in mind, this value here, that's the mean for the USA. This is the mean for China. This is the mean for South Africa. This is the mean for Germany. And then we have the mean for Argentina. Okay? So those are means for each of those countries. And likewise, we have the sample standard deviations for each one. Okay? So now, given that the actual mean for all users is 32. Now, when they're talking about that, all users, they're talking about all Instagram users, not the Instagram users from the US, not the Instagram users just from China or whatever. They're talking about all Instagram users in the world. The actual mean is 32 and the actual standard deviation is 4. So you can see how these means for each country individually are different than the actual mean. Okay? Well, if we add each value of x bar in the third column, okay? So, in other words, what we're going to do is we're going to add up all of these means here. And if we add all of these up, that gives a total of 145. Okay? And then if we take the 145 and divide it by 1, 2, 3, 4, 5, that gives us an answer of 29. Okay? All right. So notice that the value of x bar changes depending on which sample is used to calculate it, just like a random variable. Okay? And that's what they're talking about here. See, these x bars, they're quite different. You see that? It depends on what sample we're using. See, in this first one, we used the sample of users from the USA. Here we used the sample of users from China, and so on. But what we did is we took all of these means, added them up, and divided by 5. All right? So then if we average the values of x bar, so we average these values here, we get a value that is close to the actual mean of the population. So you can see how this mean here is closer to the population mean of 32. Okay? All right, so by averaging the x bar values from each country, we are effectively increasing the sample size, which in turn gives a better approximation of the true mean of the population. All right? We will see the full extent to which this is realized in the next section. All right, so here we'll look at the central limit theorem. All right, so first let's look at this. If we treat the sample mean and sample variance like random variables, they too have distributions. So let x1, x2, x3 all the way to xn be a sample from an unknown distribution with mean mu and standard deviation sigma. Then the expected value of x bar is equal to mu, the population mean. And the variance of x bar is sigma squared over n. This theorem tells us that the expected value of x bar is mu no matter what the underlying distribution is. Likewise, the variance is sigma squared over n. Provided we have slightly stronger assumptions, we can say the following. Let x1 to xn be a random sample from a normal distribution with mean mu and standard deviation sigma. Then, for any sample size x bar is a random variable with mean mu and standard deviation sigma over square root of n. Note, this theorem guarantees x bar to be distributed normally even if the sample size is 1, 2, 3, or so on. Clearly, for n equals 1, then x bar equals x1 is distributed normally. So x bar equals x1 is distributed normally, but it is interesting that for other small values that the statistic is still normally distributed. Okay. Lastly, the following states that if the sample size is large enough, then the underlying distribution is superfluous. All right. So here's the central limit theorem. Given a sample of n values from a distribution with mean mu and standard deviation sigma, then for sufficiently large n, x bar has approximately a normal distribution with mean mu and standard deviation sigma over square root of n. Okay. All right. All right. So the phrase sufficiently large will be taken to indicate samples that have at least 30 data points. All right. So using the data from example 4.1.0.1, okay, that's going to be this example right here. All right. It says find the probability that from a random sample of 200 users that the average number of times people check their feed is greater than 40. All right. So what are we looking for? We're looking for the probability that X bar is greater than 40. All right. So we've got to do what? We can convert this to a z-value. We can use a normal distribution. We have n equals 200. Okay. So find the probability that from a random sample of 200 users. Okay. So you can see here n is greater than 30. All right. So this is equal to the probability. And now let's convert this. So this right here, converting this, that was in the last section. So we've got what? 40 minus what? 40 minus 32. Okay. So the 32, and keep in mind we're going to use the 32. That's mu, and then for sigma, that's what? 4 over the square root of n, which is 200. Now, remember, they gave us that in this problem here. There's the 32, and there's the 4, mu and sigma. Okay, so we've got x bar minus mu over sigma divided by the square root of n. If you remember, in the last section, when we were dealing with the normal distribution, it was to convert to a z-value, it was what? X minus mu over sigma. Okay, but remember up here, it says for the central limit theorem and standard deviation, sigma over square root of n. Okay. And see, and notice in this problem, they don't tell us it's a normal distribution either. Okay, so now we've got to look this up. So this should be probability that z is greater than that. So this is the probability that z is greater than 28. So remember, if you look at that, there's 0 and here is z equals 28, and we're looking for the area to the right. So that means we have to do 1 minus, and remember when you look up the 28, that gives you this area here to the left. So if we do 1 minus this area, that'll leave us with this area here, because the area under the entire curve is 1. Now, obviously, I mean, we're gonna, when we look this up, so if we come down here and you can see that there's no 28 on here. This table just goes up to 3.49. But if you notice down here, it says for z values greater than 3.49, use 1 to approximate the area. And that's giving you the area to the left of that z value. So, so the area to the left here is actually 1. And so that's just going to be 0. And I mean, no, the area is not this area here is not exactly 0, but it's so small that we say it's 0. If you wanted to see exactly what this was, you could actually plug this, find the probability that that z is less than 28, probability that z is less than 28. Okay, because that's what we're doing. We're doing 1 minus that, right? The probability that z is less than 28, that's this over here, and we're doing 1 minus that, okay? And if you put this into Excel, you would see that you would get something close to 1. You may have to tell Excel to increase the number of decimal places to actually see it, but give it a try if you're bored. And that's really all that this is. I mean, this class doesn't get deep into this, so if you want to get more in depth into this stuff, you can watch some other videos for that. But that's about all it is to this class. All right, so I hope this made sense. Hope it helped. Give me a like, share, and subscribe. Thanks for watching.